Okay, so let's look at the calculation of the statistic. It is just like the other statistics that we have been calculating, the z, the one sample t, the two sample independent t. We are basically creating a ratio. So the top number is the differences between groups. And we're going to say, we're going to say that difference is because of the independent variable. And then the bottom number in the ratio is the differences that are within groups. Individual differences, measurement and error, that kind of stuff, all the differences that are due to chance. So in order to reject the null, the differences between have to be significantly bigger than the differences within. So the obtained value has to at least be more than 1, right? The top number, the differences between groups due to the independent variable, needs to be bigger than the bottom number, which is just the error measure. And then that error measure goes into the top number more than once, and thus we would have to have it at least be greater than 1. And so the question becomes, well, how much greater than 1? And that's when all of our critical values come in and comparing our obtained value to it and to decide, yeah, that's big enough greater than 1 to say that's a significant difference. Okay. All right, so let's look at the study that the textbook walks you through. I'm going to walk you through it with a 0.01 and a 0.05 alpha level, both of those, and then we'll do the confidence intervals and the effect sizes, and then we'll write it up in APA format. So the example in chapter 10 is about how long kids read when a teacher is present than when a teacher is absent in a room. Okay? So the experimental hypotheses are that there is no relationship between the teacher's presence and the time spent reading, and you can see that that is a two-tailed hypothesis. And the alternative is saying that there is a relationship between the teacher presence and the time spent reading. The statistical hypotheses that go with that is that our sample difference, mean difference, is just 0. It represents a population mean difference of 0, meaning that since there's no relationship, the kids read just as long when they're with the teacher as when they're not with the teacher. So the overall difference, or the average difference, would be 0. And then the alternative, and again, because it's two-tailed, there is a relationship. When the teacher's in the room, they read a certain amount, and when the teacher's out of the room, they read a different amount. And thus, we have a non-zero difference in the alternative. Now we have to set the criterion. Remember, we have to think about, well, what is alpha error, what is beta error, and which one is worse? So an alpha error would be saying that teachers present or absent is going to affect how long a kid reads when it really doesn't. That's what the error is that we're saying one thing and that's really not true. Well, depending on what we find, we could be wasting the teacher's time by saying, yeah, you have to stay in the room because the kids will read longer, and it really isn't making them read longer at all. Or we could make them stay out of the room because we say, hey, when you're out of the room, they're going to read longer, when they really don't. And meanwhile, kids are getting into all kinds of trouble and acting up, and that just sounds like a bad thing. So we might want to avoid an alpha error and set it at 0.01. But we have to think about what a beta error is before we make that decision. So a beta error would be saying the opposite. It would be saying, it doesn't matter whether the teacher is there or not. The kids don't read any longer whether she's there or not. But it is really true that they do read longer when the teacher's there or when she's not. We haven't found that out yet. We just know that her status might affect how long they read. Well, if kids actually read more when the teacher's present, and we say, oh, it doesn't matter, then we're missing out on an opportunity to have them read longer. If the kids read less when the teacher is there, then we could also be missing out on an opportunity to have them read longer, because we wouldn't then be telling the teacher, oh, you've got to leave the room because the kids will read more. But when we think about the consequences, I'm more worried about child safety, and I can always use other strategies for increasing reading, getting them more interesting books. There's other strategies. So I am going to try to avoid alpha error and set it at 0.01. Okay? Now that's a problem because of power. I've already got a two-tailed hypothesis, and that's less power. Now I'm setting the alpha level low, and that's less power. So I'm a little concerned here. But let's look at our research design. So since I'm thinking about power, I am going to use a repeated measures design to try to get that power back. Okay? I am going to have 8 kids in a room and give them a book with the teacher in the room and measure how long each one of them reads during a 6-minute session. Then I'm going to wait a day or so, give those same 8 kids a book and ask the teacher to leave the room and then measure how long each one of them reads during a 6-minute session. I'm going to make sure that there's no other adult in the room, so I'm controlling, adult presence by being behind a one-way mirror. So now let's look at the power. Okay, so I'm manipulating the independent variable. I'm having the teacher in the room, and I'm taking the teacher out of the room. With 4th graders, I think that is a big difference experientially. So I'm going to say that I am using very different levels of the independent variable, and that increases power. When I look at how I'm measuring the dependent variable, I am measuring time spent reading. So I'm using a timer, and I'm sure it's a really accurate timer. So I'm also using a ratio scale, meaning, 0 means they didn't read at all. And so I've got a really good measure of my dependent variable. So I think I've got some pretty good power strategies there. However, I do only have 8 kids. So that's a small sample. Even for related samples, it's small. So I'm back down. I've compromised power again. So I've got 2-tailed hypotheses. That lacks power. I've got an alpha of 0.01. That lacks power. I have small samples. That lacks power. I did greatly manipulate the independent variable. That gives me power. I have a really, really good measure of the dependent variable. That gives me power. And I am using related samples. And so there's some power in there too, even though I've got small sample sizes. So let's see what happens. I'm going to conduct the study, collect the data. Here's my data. And so I put the scores in under both of those conditions, and then I click on data. Remember, you have to have downloaded that data pack. Click on data. Step 2, I'm going to click on data analysis, which brings up that dialog box. And then I'm going to click on t-test paired 2 samples for means. And then I'm going to click OK. When I click OK, I get this additional dialog box. So I'm going to put my cursor in the box where it says variable 1 range, and then I'm going to highlight all the data in the first condition of the independent variable. Make sure you do not highlight the words or you're going to get an error message. Just highlight the numbers, and you'll see that the location gets put into that box. Then I'm going to put my cursor in the next box and highlight the second set of data, which tells that dialog box where that data is. I'm going to put the value that's in the null in this box here, and then I'm going to make sure to set my alpha level. Then I'm going to click OK, and I've got my output. Make sure that you expand the columns so that you see all of the words and the numbers. Your t-stat is your t-obtained. It's 2.806. Down at the bottom, the very bottom one, we do have a 2-tailed test, so we have to look for the t-critical that's 2-tailed. It's 3.499. So my obtained value is less than my critical value. I have to fail to reject the null. Okay. Let's look at setting the alpha level at 0.05. So I had to go back and I just redid the analysis, setting the alpha level at 0.05. My t-critical changed. It moved in. Okay. It's farther in, thus allowing my t-obtained to be out there in the region of rejection. My t-obtained is still 2.806. Now my new t-critical is 2.364. My obtained value is greater than my critical value, so now I can reject the null. So I'm going to continue with this example because I want to show you how to do confidence intervals and effect sizes. So let's say we have rejected our null at the 0.05 level, and now we want to know, well, how much of an effect does teacher status, present or absent, have on student reading? And I can do my Cohen's d. The Cohen's d is a ratio of the mean difference over the standard deviation. Okay, I can put mean difference minus 0. It's still going to then be the mean difference. So I have to get my standard deviation. Well, where do I get my standard deviation of the difference scores? go back into Excel. I have to compute all of the differences. So I have, let me click all this. Nope, I don't have, okay. So I have to compute all of the differences. So it's present minus absent. That's a difference of 10. Present minus absent for each person. And now I have a data set of difference scores. Now I'm going to click on formulas, then click on more functions, then click on statistical, then go all the way down to stdev.s. So it's the standard deviation of a sample. And then click on that, and I get a dialog box. Put my cursor in where it says number 1, then highlight all the numbers, all the D's, because that's what I want the standard deviation to be. I want the standard deviation of the differences. Once I highlight all those, then my standard deviation shows up, and I can round that to 2 places. Okay, so that's where I find my standard deviation of the differences. Back to effect size. So I'm looking at how much longer do kids read when their teacher is present versus when the teacher is absent, because that's how I computed my difference scores, present minus absent. Computed the Cohen's d. It winds up being 0.99. According to the textbook, that's a large effect size. So students, when the teacher is present, read almost a full standard deviation longer than when the teacher is absent. The standard deviation is about 15 seconds long, so they are reading about 15 seconds longer. That is statistically significant. Now we want to talk about, well, how much does teacher presence account for reading time? And that's when omega squared and eta squared come in. So here's eta squared. It's just your t obtained squared over your t obtained squared plus degrees of freedom. And when I compute all of that, I get about 53%. Remember, that's a proportion of variance accounted for. So I can say that 53% of the time that children spend reading is accounted for by the teacher being present or absent. Okay. If I want a more conservative estimate, I'm going to do my omega squared, which is, again, the t obtained squared minus 1 over t obtained squared plus degrees of freedom. It is a smaller proportion because it is a more conservative estimate. And I can say the same thing. So because we did an actual experiment, we can change the wording a little bit. And we can say that the teacher's presence or absence actually caused about half of the change in the student's time spent reading. And we can be pretty confident about that because we did do a repeated measures design and thus eliminated everything else that may have caused them to read different lengths. So the only difference between the first group and the second group was the teacher's presence or the teacher's absence. So with this proportion of variance accounted for, we have one variable that's accounting for half of the change in reading length. So we just have to look around and see if we can find another variable that explains that much. And we've pretty much got length of time spent reading fully explained. Now we can do our confidence intervals. When we want to tell somebody, well, how much of time can we expect kids to read longer when the teacher is present? Well, we did find it was 15 seconds, but remember that's a point estimate, and you're much better off going with a range. So with our alpha of 0.05, let's compute a confidence interval that we can be 95% sure that the difference in reading length is in there. So we have our t critical at the two-tailed level for the alpha that we tested our hypotheses at. We have our standard deviation, our standard error of the mean difference. Standard error of the mean difference is to take that standard deviation that we computed a couple slides back and divide it by the square root of n. And then we add it to our mean difference, and we get 27.65. We subtract it from our mean difference as well to get the lower level, and we can say that kids will be reading anywhere from about 2.35 seconds to 27.65 seconds more when the teacher is in the room. And we're 95% sure of that. Okay. When we look at the confidence interval, it does not contain 0, and it shouldn't. We've already rejected that as a possibility. So